Great, wonderful. Welcome to everyone online. Welcome to everyone who's in person. You could probably take your mask off if you don't want to wear it, just because we're not super crowded this morning. We are starting a new unit now, Unit 12 on chemical equilibrium. We're actually moving through pretty quick. I'm happy with the pace we're going, and I'm not worried about getting behind. I had mentioned in a couple of previous classes about the possibility of us maybe using our class time for things other than lecture now and then. And so one thing that I have kind of arranged for anyone who's interested and local is using a class time sometime in the coming weeks to do a tour of the Acadia lab for agri-food and beverage. So what that is it's a lab that's in the pavilion, which is sort of connecting Elliott with Huggins. And it's a lab that has about $2 million worth of new equipment in there the government has funded. And the purpose of this lab is to provide chemical analysis of wines, beers, things like that, that are produced locally. And this is to support the industry to help it grow faster and have products approved for export and this kind of thing. So they have a lot of fancy equipment in there. All of them are doing chemical analysis based on chemical principles, many of which these principles are things that we're learning in the course. So I think it's appropriate. I think there's reasons why you might be interested. First of all, to kind of see what state-of-the-art chemical equipment looks like. Even if you were able to do labs every single week in first year, the equipment that you end up using in first year is maybe more limited. We don't have millions of dollars of equipment for every student in first year. So this might be an opportunity to get your hands on some of that. Also, we've had a number of chemistry students in recent years do co-op terms there. So if you're thinking co-op might even be a remote option for you, might be nice to just to see what happens in a place like that. And I'll let you know more about that. So that's kind of arranged. I think it's the 25th that I've set that up for, which is a Wednesday. But don't quote me on that. I'll get more details for you in a bit. What else? We have a new assignment. Well, not really new. It was out Wednesday. Yeah. So I haven't heard any problems with that yet. So if anything comes up, let me know. That will be covering the previous unit. We're kind of doing a unit a week, it seems, lately, which is good because, yeah, leaves us a little bit more time for these other things, which is great. Especially important this year, I think, because lab experiences are few and far between. And I don't mean just here at Acadia. If you are at many schools, you wouldn't have anything. Samantha asks, when is our first midterm? I looked at this yesterday because I wanted to make sure myself. I think, don't quote me, March 3rd is my guess. Let me quickly look that up. Remember, there's two. There's a midterm, and then there's going to be an oral exam the following week. Just one midterm, yeah. Plus 2 quizzes, yeah. That'll be it. Open. Okay, so our midterm, okay, February 27th, which today is the 12th. So yeah, 15 days from now. And I just want to make sure that matches what I've said before. My intro slides. Okay, I've got March 3rd here. Let me go back and clarify that. I have midterm on March 3rd, oral quiz week of March 7th on my intro slides. So there's a disagreement there. I do have a calendar set up where I have the midterm on March 3rd. So I'd say March 3rd is our midterm, not February 27th, which is a Saturday. So yeah, our midterm will be March 3rd. I can confirm that now. And the following week, which will be the March week, starting March 7th, which is a Sunday, but we'll go Monday, which is the 8th to the 12th, is when we'll do the oral exam. So we'll have a sign up where you can pick a time. And hopefully that'll help me get to know you guys a bit better, because it's a little bit hard for me to do that in this kind of situation. Yeah. So definitely, I'll fix that intro, the syllabus that's up there. But yeah, March 3rd, which is a Wednesday. Quiz. I think I said in the email that it was due yesterday at 5. It was due today at 5. I don't know what's going on with me, but yeah, it's always been today. I think I just made a mistake on that email, but yeah, you have until today if you haven't done it already, and please make sure you do it. I can actually take a peek at that right now to see how many people have done it. So 9 people have done it. There's more than 9 people in this class. So yeah, if you haven't done it, do it. Okay, great. Let's start our material on chemical equilibrium, which is the next unit. And as I said yesterday or Wednesday, I know that you guys have looked already at equilibrium last semester in the context of acid-base equilibrium. We're going to expand on that just a little bit and connect it to what we were talking about in the previous unit with Gibbs energy and with entropy and enthalpy and all these thermodynamic terms. And a few things that I think you probably already know, but we can just reiterate them quickly. An equilibrium is what we call a dynamic equilibrium, meaning although concentrations of reactants and products are not changing when a system is at equilibrium, there is still forward and reverse reactions taking place. So if you look at an example here of like salt sitting in water that's saturated with sodium chloride, the amount of salt that's dissolved in the water does not change over time. It doesn't increase or decrease, but there's constantly ions that are being dissolved off the surface of the solid salt sitting in the water. And there's, at the same rate, ions in solution that are being deposited back onto the surface. There's no net change, but there is change. It is dynamic. There is still motion. It's not still. So chemical equilibrium, all chemical reactions, I guess, in principle are reversible, but in many examples, the reaction is not practically reversible. An example, like if you burn a piece of paper and some of the products are gases and leave the situation, obviously that can't be reversed if the products are gone. Also, if you have a very complicated structure like paper, chemically speaking, it's a very complex structure. It's very difficult to remake that complex structure using a pathway like combustion in reverse. But in principle, it can go forwards or backwards. And we can say that at equilibrium, when the system is at equilibrium and there's no net change anymore, the forward rate and the reverse rate are exactly equal to each other. Okay? Which makes sense. If the forward rate and reverse rate are exactly equal to each other, then there won't be any net change, which is what we see. So it kind of looks like this. You could take a reaction, take a system, and there'll be a forward rate. And as the reaction proceeds, the forward rate slows down according to this red line, which is what we would see in many examples, right? We'd see this sort of exponential decay if it was first order or second order. The reverse rate then increases as you start to generate products. And eventually those two rates equal out. And when you hit that state, we're at equilibrium. All right. So forward rate and reverse rate are equal at equilibrium. We can define something called the equilibrium constant, sometimes called the thermodynamic equilibrium constant, only because sometimes the term equilibrium constant or equilibrium gets used in areas where it's not rigorously defined. So we're going to be using the rigorous thermodynamic definition of equilibrium constant. We're going to introduce the very rigorous one and use a more practical version of it. The definition of that is the rate constant for the reverse reaction, forward reaction divided by the rate constant for the reverse reaction. So remember, the rates are equal, but the rate constants are not equal. Okay? So if you can measure the rate constant for the forward and reverse reaction, you can get a measure of K. There's another version of the equation for the equilibrium constant that we use much more commonly. And probably what you're used to maybe is like equilibrium constant equals concentration of products over concentration of reactants. And if a product appears more than once, you would put a superscript 2, 3, 4, and reactants 2. And that's really a simplification of this form of the equation. Now, in thermodynamics, whenever we use concentrations, what we should be using, if we wanted to be rigorously correct, is another measure, which is called activity. And activity, it's like concentration, except another way to say it, it's like the effective concentration. So sometimes if you have very small amounts of something or very large amounts of something, you get these weird concentration effects where, for example, if you're at a very high concentration, you might have the things that are dissolved in water pairing up and forming clusters, and they don't behave anymore like their actual concentration would dictate. And in those situations, what we can measure or define is something called effective concentration, where, you know, at those extremes, this system is behaving in a different way. So we call these things activities. The thing is with activities, and I think if you go up into higher level chem courses, you'll spend a lot of time looking at those situations where the activity of a dissolved substance or a gas is different from its concentration. But in this course, we're going to make the assumption that every time we see activity, we can substitute activity for concentration. Now, the nice thing, I guess it's a nice thing, these activities that we're talking about are unitless. So they don't have actual units. So when you express an equilibrium constant, which is just a product of all of the activities of the products raised to the power of their stoichiometric coefficient, divided by the product of all the reactant activities raised to the power of its stoichiometric coefficient. So if you had a reaction, A plus B is in equilibrium with 2C plus D, then you could say that the equilibrium constant there is going to be the activity of C squared times the activity of D divided by the activity of A times the activity of B. Now, this looks like the equation that we normally use using concentrations. And for this course, we're going to just use concentrations here. But I want you to just be aware that when we put concentrations into this equation, you know, our simplification is going to be that activity is basically the same thing as concentration, which, yeah, is not true at extremes. So we would say then this would be now in this situation, there should be no units because technically we're supposed to be using activities here. Activities don't have units. And for that reason, we are going to end up with K, which is a unitless number as well. It's a constant, but there's no units attached, not in units of moles per liter or something like that. So just be very aware that this version that we will be using, and is probably the version you've been using all the way up to this point in time, is a simplification of the actual correct form of that same equation, using the assumption that we can substitute concentrations in for activities, which at normal concentrations and normal pressures is an okay assumption for us to make. But one result of this is that our K that we're ending up with at the end does not have units. The other thing that I wanted to mention about activities is the activity of a substance that is a pure liquid or a pure solid is defined as, that's an A, as 1. Okay. So if you have an equilibrium that involves solids or liquids, if there's gases present, we would say that the solvent themselves have an activity of 1. Great, so we're going to simplify things. We're going to use this form, realizing that we leave the units out. The units that we use for the concentrations are moles per liter. We just don't use those units when we're calculating K. And so what K really is a measure of how far an equilibrium lies to the right or lies to the left. So think about this number. If the equilibrium produces a lot more products than it does reactants, then this number is going to be big, and this number is going to be small, so K is going to be large. So a large value of K, any value of K that's greater than 1, is going to indicate a situation where the products are favored over the reactants. And vice versa, if the products are low in concentration compared to the reactants, it favors the reactant side, and K is going to be a smaller number, less than 1. K can never be negative. You can't have negative concentrations. The smallest concentration you can have is 0. And technically speaking, every reaction can be explained with a equilibrium constant. So a reaction that lies very, very far to the right. So let's say you have, I don't know, a piece of paper on fire, and you put that in a box, you light it on fire with lots of oxygen, that'll burn and make products. That technically will have a K value associated with it, although the K in that case is probably going to be a very large number, like 10 to the 9 or something like that. It's going to lie very, very heavily on the side of the products. All right. So we have different types of K that we often use. You may remember using Ka and Kb last semester for situations where the equilibrium involved an acid dissociation or the reaction of a base to produce hydroxide. Generally speaking, we can call those examples of Kc, where it's the equilibrium constant when we're expressing concentrations. So remember, we're always using concentrations in these cases. That's Kc. Ka we use for acids, as we know. By the way, when we use acids, just look at this equation for a second. Notice that pure water does not appear. And the reason for this is everything else is a dissolved substance present in some small concentration. The water, though, is the solvent. It's a pure liquid. I mean, I guess it's not pure because there's other stuff in there, but in this example, it's a pure liquid, and pure liquids have an activity of 1. We talked about it a few slides ago. So, I mean, you could put technically in this equation the activity of water, but that's just 1, so it falls out. And sometimes I've seen textbooks. This is a bit of a tricky little point here, a very minor point that some people care about, some people probably don't. But some textbooks I've heard some professors say, oh, we just drop water out and the value just ends up as part of the equilibrium constant. That's not true. Water, the activity, it's because we're supposed to be using activities, and the activity of water is equal to 1. Why it's not there. All right, so we have Kc, Ka, and Kb are forms of Kc or specific instances where we use concentrations. The other thing we can use is pressures, partial pressures. And this is what we would use if the equilibrium involves gas phase things. So in this example, we have, A plus B, two different gases in equilibrium with C plus D. Everything here is in the gas phase. So in that case, what we can do is use Kp, and there, as a proxy for activity, we're going to be using partial pressures in units of bar. And so these are sort of the defined thermodynamic constants, Kp or Kc. You can only have Kp if you're using gases, obviously. You can't use pressures if you're in solution, for example. But if there's gases present, Kp is the correct one to be using. Cool? Great. Everyone's with me here. Heterogeneous just means not all in one phase. So you have multiple components here to a reaction system, which are potentially in different phases. An example, we have this equilibrium situation where we have calcium carbonate, which is a solid, which is in equilibrium, calcium oxide as a solid, and carbon dioxide gas. Now, solids have an activity of 1. So our expression will ignore those. If you have a heterogeneous equilibrium like this and you have gases and solids, we just ignore the solids because solids have a defined activity of 1. And so they don't contribute or they don't appear in the ultimate equilibrium constant. So in this example, the Kp would just be the pressure of carbon dioxide and nothing else. The position of this equilibrium completely depends only on the pressure of CO2, not on the pressure of anything else. So if you wanted to push this reaction to the left and create more calcium carbonate, you could just increase the pressure on the CO2. Great. That simplifies things a little bit in these situations where there's more than one phase happening. I think we talked about that already. Write expressions for the equilibrium constants for the following reactions. Okay, so here we have in A, N2, which is a gas, plus 3H2, which is a gas, in equilibrium with 2 ammonias, 2NH3 gas. So the way we would express the equilibrium constant here, so you have Kp, which is the K that we would use in a situation like this, preferentially. It would be the pressure of NH3 in bar squared. And we square it because of the coefficient that's in front of it right there. We divide that by the pressure of N2 multiplied by the pressure of H2 cubed. And the cubed comes from the 3 in front of the H2 that's in the balanced equation that you see right there. Okay, B. B looks like an acid-base equilibrium to me. And because these are dissolved things in water, we would use a Kc. And in fact, the specific type of Kc in this example is Ka. And that's going to be equal to the concentration of the products times H3O plus divided by and we forget about this because activity of liquids, pure liquids like this is 1. Does not appear in the equilibrium expression as a result. Great. The last one we just looked at on the previous slide. We have Kp because we have gases. And it's just the pressure of CO2 because everything else is a solid, different phase, activity is equal to 1. Great. Problem. The following reaction comes to equilibrium with partial pressures pH2 equals 0.81 bar, Pn2 is 1.20 bar, PnH3 is 0.15 bar. Calculate the equilibrium constant under these conditions for the following reaction. So our Kp is going to be equal to the pressure of NH3 squared divided by pressure of N2 times pressure of H2 cubed equals pressure of NH3 0.15. I'm going to leave the units out because really this should be activity, which is unitless. Pressure of N2, 1.20 bar, and H2, which is 0.81 bar cubed. And the answer is a number, which I have somewhere. Come on, PowerPoint. 856, so we're doing pretty good. .0353. So notice this value of K is pretty small. It shows that under this set of conditions, the reactants are greatly favored over the products. This is, you might just look at this and say, yeah, okay, here's some chemical equations. Let's take these chemicals and stick them in a formula and get a number and be done with it, which is really all I'm asking you to do. But this actually is probably the most important chemical reaction that we know of that's an industrial chemical reaction. This is called the Haber-Bosch reaction, or sometimes just called the Haber process. And a significant percentage of the energy that we produce on Earth through oil and gas and nuclear and everything else is spent doing this particular reaction. And what this does is it takes nitrogen out of the air and it combines it with hydrogen gas. And we have a process for getting hydrogen gas called steam reformation. And by combining these two, you get ammonia. And that's really hard to break, the triple bond of nitrogen. So it's a really difficult process. This equilibrium greatly favors the reactant. So it's very difficult to make much of ammonia this way. But the good thing is if you take ammonia and you burn it, this just is just simple meaning oxidize. We can get NO2. And if you react that with water, you can get HNO3, which is nitric acid. If you take NH3 plus HNO3, you get NH4NO3, which is ammonium nitrate. Anyone know what ammonium nitrate is? Two main uses for ammonium nitrate. One is it's an explosive. The main use, though, is it's a fertilizer. Fantastic fertilizer. This process was developed about 100 years ago, maybe 120, somewhere around there. And once this process was discovered, basically it allowed us to make an unlimited source of fertilizer. And the world's population basically increased by like a factor of 10 when this process came into being, because it allowed us really to grow as much food without worrying about stripping all of the nitrogen out of the soil and then having the soil not provide food anymore. So it's allowed us to produce the amount of food we're producing now and supporting the population we're supporting now. So from that perspective, it's an extremely important reaction, and it's one of the few ways we know of taking nitrogen out of the air and turning it into a usable form of nitrogen that growing systems can take. There's a stat somewhere, like the human body has lots of nitrogen in us in our proteins, and there's some large fraction of the nitrogen in our bodies that's produced synthetically using this process. Like, I don't know what the number is, like 50% or something like that of our nitrogen comes from this particular process. Yeah, but it's a very important. Nitrogen is a really important element for life. And if you can get a source of fixed nitrogen like this, that's very important for growing systems. I remember when I lived out west, there was all these rivers that would come in from the ocean. I guess they don't come in, I guess water goes to the ocean. But salmon would come up the river to spawn, and they go up like miles and drop all their eggs. And it was very spectacular at the time of year in the fall when you go and you'd see all the fish. And it was also a time of year, great time of year for lots of other animals, like lots of birds, lots of like bears would come and feed on these fish that were just basically sitting ducks. Like there was hundreds and hundreds of fish, and you could just watch them all in the water. It's like they filled the whole thing. And what they found is that on the edges of these rivers, for about like a kilometer on either side, the trees were far more lush, they were taller, they were stronger, they were growing much faster than they were in the rest of the forest. And what they figured out was over years and years, birds would grab fish out of the water, fly into a nearby tree and eat at least some of it or most of it or whatever, drop some on the ground, or defecate on the ground or whatever it was. But what was happening is the animals that were feeding on the fish were bringing that nitrogen out more broadly away from the river. And of course, that effect, the further away you got from the river, got weaker and weaker. So it was believed at least that these fish were the main source of nitrogen to fertilize the forests coming in. So they weren't just important for animals who were eating them for food, but it was also important to support the entire forest ecosystem as a source of nitrogen. Cool. Okay. So on this slide, really what we're talking about is what happens to a equilibrium constant when you modify the chemical equation that you're describing with. So in that previous example, we used this balanced equation to talk about the value of K. If you reverse this equation, if you write it in reverse, which we can do with any reaction, you can write this one in reverse. What happens is you would write this as now the equilibrium constant for this new reversed equation would just be pressure of nitrogen times pressure of H2 cubed, which are the products, divided by the pressure of the reactant, which is NH3 squared, which is just 1 over the form that we had up there. So what this means is if you take an equation, you write it in reverse, the equilibrium constant for the reverse reaction will be 1 over the equilibrium constant for the forward direction version of it. So if you can flip an equation back and forth, you just have to take the reciprocal of K. If you take an equation and multiply everything by 2, like we've done here, basically we just took everything here and multiplied by 2, the equilibrium constant for that new reaction is going to be your original one squared. Okay. So you can multiply all of the coefficients by some number, and all that means is the K will be raised to the exponent of whatever you multiplied that original equation by. So these can be useful because sometimes you can figure out equilibrium constants for equilibria you don't know yet using existing equilibrium constants and adding and subtracting different equations. So we might see some examples that look like that. So here's an example. Let's say we have two equilibria. A plus B is in equilibrium with C plus D. We could define an equilibrium constant K1 for this reaction 1, which is the product concentrations divided by reactant concentrations. Now we have a second equilibrium where the products of the first one, C plus D, form an equilibrium with E plus F. So we have a K2 for that scenario as well. What we find is if you wanted to look at the overall equilibrium, A plus B in equilibrium with E plus F, what we're doing is basically just adding these two together, canceling what appears on both sides, do an addition to give us the reaction. Our overall K is going to be, well, we could just say this, our K is going to be E F over A B from this equation, which is equal to K1 times K2. So if we add two equilibrium expressions together, the new equilibrium constant is going to be the product of the two equilibrium constants that we began with. So this slide, coupled with the previous slide, allows us to determine equilibrium constants for equilibria using existing ones if we can add and subtract those expressions together. And as we'll see, this is because equilibrium constants are a product of delta G, and a delta G is a state function. Depends on the initial and final states, not how you get there. So we can add and subtract these equilibrium constant or reactions, multiply together the constants, and we get new equilibrium constants for the overall thing. Yeah. Let's look at an example. We have N2O gas plus O2 gas is in equilibrium with 2NO. What's the equilibrium constant for that, given the following two equilibria with the following two equilibrium constants? First one, N2 gas plus 1/2 O2 gas is in equilibrium with NO gas. K1 is 2.7 times 10 to the minus 18. So think about that number for a second. That's an extremely small number. That number indicates that that equilibrium greatly favors the reactants. Super small number means reactants are going to be favored. There's going to be essentially no N2O in that particular example. The other reaction is N2 plus O2. That's also a very small number. In fact, even smaller, 4.7 times 10 to the minus 31. So what we want to be able to do is manipulate these two equilibria, combine them in a way to give us this overall equation. If you look at the bottom one actually is already in pretty good shape, because as a product we have 2NO, and as a product up here we have 2NO. What we have to do, though, in that first reaction up here, reaction 1, is we have to invert it if we want to add it to the second one and have it cancel out to give you the top one. So let's rewrite reaction 1 where we just invert it. We'll call it 1 prime. So this becomes N2O gas is in equilibrium with N2 gas plus 1/2 O2 gas. And that new K is going to be equal to 1 over K1. So when you invert an equation like that, you have to invert K as well, take the reciprocal. Now what we want to do is take 2 and our new 1 and add these together. And what we would get is the N2 cancels on both sides. The half O2 over here cancels with half of the O2 there to leave half on the left. And that leaves us with N2O gas plus 1/2 O2 gas is in equilibrium with 2NO gas, and that's it. So our K in this example is going to be our K2, which we haven't modified. So we left the reaction written as it was, multiplied by 1 over K1, which is just K2 over K1. Okay. So that new K, let's move that up here. Equals 4.7 times 10 to the minus 31 over 2.7 times 10 to the minus 18. And then we can get the equilibrium constant for that new expression as well. And the value of that is 1.7 times 10 to the negative 13. Still very small, not as small as either of the individual ones, but still it tells you that this equilibrium will greatly favor the reactants over the products. Great, no problem. Okay, so what we're going to do now is try to bring what we've just learned about equilibriums, equilibria, and equilibrium constants and connect it to what we've been doing in the previous units, talking about Gibbs energy. So what we know is that Gibbs energy for a reaction is really the driving force to push the reaction forward. And if we have a delta G that's negative, we say the reaction is spontaneous in the forward direction. If you have a reaction where the delta G is is positive, it means the reverse reaction is going to be spontaneous and the forward reaction is non-spontaneous. If delta G is equal to 0, if you have delta G of 0 Gibbs energy, that describes a system where you're at equilibrium. There's not a driving force for this to go forwards or reverse. Now, in this situation, when you have an equilibrium situation like that, we can describe that with a graph that looks like this, where the y-axis is Gibbs energy, not delta G, but Gibbs energy. And you're looking at sort of a case where we're going from sort of 0% reaction to 100% reaction, where on the left side we have 0 product and all like 100% reactants. And at the other extreme, you have none of the reactants left and 100% product. So you can kind of see this graph going in this direction is a bit of like a progress bar. How close to the 100% products are you, or how close to the 100% reactants are you? And if you have a reaction that has a negative delta G, then we would say that this is a reaction that is spontaneous in the forward direction. So this blue line here is representing a reaction with a negative delta G, because delta G will be whatever that arrow is. What will happen in this example is the reaction, we start up here with all reactants and no products. As the reaction goes forward, you start to form products and use up reactants, and the driving force to continue going forward gets smaller and smaller, right? So if you get to, let's say, this point, we would say that our delta G to continue forward is half or less of what it was going forward. And it'll continue. It wants to minimize its own internal energy. It follows that path all the way to the bottom. And when you get to the bottom, then you are kind of stuck. You're at the minimum energy, which is the system is always trying to get to the minimum energy. It's uphill to go either to the right and make more products, or to the left and make more reactants. So we say, you know, we're in the most stable place where this system can be. It's not spontaneous for it to proceed forward, nor is it spontaneous for it to proceed in reverse as well. So that situation is what we would call the equilibrium. The equilibrium position is the minimum Gibbs energy that this system can attain. And when you hit that equilibrium point, there's no driving force to go forwards or backwards. And that's why you don't see any net change once you get to that equilibrium position. So this is an example of a reaction with a negative delta G, which we know that means spontaneous in the forward direction. And you can see that the equilibrium position here favors the products, meaning it forms more products than it does reactants. Many reactions that we see that would have very large negative delta G values, like, I don't know, let's go back to our burning the sheet of paper. That's exothermic. It proceeds very rapidly under the right conditions. If you have pure oxygen, it's super fast. That might have a curve that looks like this, where the minimum is extremely close to 100% reaction. Okay, so this example that we have here is, you know, a little bit more off towards the middle, but many reactions that are very exothermic, very spontaneous in the forward direction, very large negative delta Gs, go to what we might say is essentially 100% completion. It might hit like 99.999% complete, according to this particular scheme that we have here. So we're going to be coming back to this, I guess not for a while, because we don't have class on Monday. So I guess Wednesday. Where we're all going with this is towards this equation, which is one of the most important and most fundamental equations in all of chemistry and physics. It provides the relationship of the position of a reaction when it's complete, when it reaches equilibrium, and shows how that's a function of the delta G. So the delta G, standard delta G for an equation is just equal to negative RT ln K. I'm not going to get any deeper into that. We're going to leave it right here. But we're going to develop this equation and concept and apply it when we come back on Wednesday's class. And until then, please have a great weekend. Note that the next assignment does have a due date on Thursday instead of Tuesday, the usual Tuesday. I just extended it because of the break. We'll get back on track the following week, though. So thank you, everybody, for coming online. And I will be posting this for the people who aren't with us right now, who wanted to sleep in. Great. So thanks, everyone, and have a great weekend.